Hey everyone, it's your favorite funny Minecrafter here, SpeedyCube64, and this is the supplementary video for the Redstone computer. Now, this video is going to teach you a couple things. First, I'll be telling you about how this computer works in a lot more detail than the main video did, including like how each of the main component works with examples. Second thing I'll be telling you is how you can actually like program this yourself. I'll also be going a little bit into how real hardware design works with FPGA boards, and also I'll just be giving you some notes on the making of the video itself. Now, a couple disclaimers before we start. Number one, this video is definitely going to be a lot less polished than the regular video because it would take me years if I were to make a highly edited, detailed video about how this entire thing worked. Number two, although I'm going into a lot more detail than the main video, this is still a very high level coverage of the Redstone computer. So if you want to know what like each individual repeater and comparator, each individual logic gate do, this still won't really explain it all. In general, if something is already in Matt Bagg's logical Redstone series, then I won't be explaining it again, but I will be telling you which episodes to watch if you are interested in learning more about that, like in depth. And number three, although I like to think I know a lot about this subject, at the end of the day, I'm still a college student, so there's a good chance I'm going to be wrong about a couple things here or there. So if there's any clarifications you need me to make, or if you think I'm wrong about something, feel free to say something in the comments and I'll do my best to try and clear things up. All right, let's get into it. Okay, so the first thing I'll be going over here is binary numbers. Now, in the game, Redstone has a signal strength that ranges from 15 being the highest, all the way down to 0 being the lowest. But when we're doing like logical Redstone, 99% of the time we don't actually really care about this. What we really care about is simply whether the signal is on and off. And when you're dealing with signals that can only be on and off, well, there's only really one way to represent numbers, and that's using binary. So instead of the decimal number system that normal people use, where every time you go to a new digit, its significance increases by a factor of 10, in binary, each digit means 2 times as much as the previous one. So, this is the ones place, this is the twos place, where in decimal a number, this digit would be the tens place. This is the fours place, this is the eights place, and so on. And the only, digits in binary are just 0 and 1. So let's say you wanted to make a number like 13 in binary. What you do is you turn these lamps on. You'd have 8, 4, and 1 because 8 plus 4 plus 1 equals 13. And the way you'd say this number is 1101 because the 8's place is on, the 8 is counted, the 4 is counted, the 2 isn't counted because it's not necessary when you add these things up to make 13, and the 1 is counted. So 1101 is how you would make 13. Now, although in this video I'm mostly going to be saying the decimal equivalents of the numbers, just to make things easier to explain and for you to understand, under the hood it's all using these same binary numbers. Everything is using binary in this computer. This computer also works with 8-bit numbers, which means that there are 8 of these like binary digits, either ones or zeros, and the maximum number that the computer can work with in this case is 255, because if you have all these digits on, they would all add up to 255. If you want more examples on how binary number systems works, then that'll be found in Logical Redstone Reloaded number 2. So the arithmetic logic unit, which is the next component I'm going to be covering, is sort of like a tiny calculator with a few extra capabilities. The ALU's job is basically to take these two numbers, A and B, and then do some operation on them, and then output the result of that operation here. And the operation that it actually does depends on this 4-bit number on the bottom called the opcode. And to figure out which opcode corresponds to which operation, you want to look at the first 12 instructions in the instruction set. The other 4 are reserved for like different components. So for these examples, I'll be setting A to 6 and B to 5. The first example I'll be going over is opcode 6, which is the add operation. And as you can see, what this does is it takes our numbers A, which is 6, and B, which is 5, and it adds them together. So in our case, the result is 11. And similarly, if you were to use opcode 7, which is the subtract operation, you'd get 6 minus 5 equals 1. The next operation I'll be going over is called bitwise AND, and this is at opcode 3. So what a bitwise AND does is it takes these bits here in like horizontal pairs from our inputs A and B, and it only turns that corresponding bit in the output on only if both of these, if this bit in both of the inputs are on. So in looking here at these pairs of bits horizontally, you can see the only time when they're both on is here in this second row here. Well, 0, 1, 2, it's bit 2, if you count up like that. So you can see the only bit that's on in the output is bit 0, 1, 2. It's bit 2. And so the result of the bitwise AND of 6 and 5 is 1, 0, 0, and that's 4. Now the last thing I'll be going over here, last example, is opcode 10, which is load immediate. And this is useful when you want a number to be immediately available for the computer to use. So in this case, you know, whatever is specified here in the immediate, this will come from the instructions, is passed straight through to the output. In this case, it doesn't matter what the values of A and B are. Now I should also mention that besides the 8-bit result of the number here, the ALU also outputs this line on top called the 0 flag, and this 0 flag is only on when the result of the operation is 0, and that's going to be useful later. The major parts of this arithmetic logic unit are an adder, or more specifically a toggle subtractor, which is orange piece here. That's from Logical Redstone Reloaded 4, and a multiplexer, this red part here, which is from Logical Redstone Reloaded 6. So next up we have the register file, and this is basically like the computer short-term memory, and each column of repeaters right here makes up one 8-bit register, which is responsible for holding a single 8-bit number. So this register file in particular has 8 registers, and each register has an address that goes from 0 all the way over here to 7. Now this register file has 2 read ports and 1 write port, which means these 2 read ports allow you to look at the values from 2 registers at once, and then the write port allows you to change the values of what's inside these registers. And the way you do that is using these addresses here at the bottom. So I'm going to show you an example. Let's say I want to put the number 6 into register 0. So what I would do is I would, on the write port, put 6. On the destination address, I have 0 here. So I'd press this write button, and that would save the 6 into register 0. And then next I'll be doing 5. I'll save the number 5 into register 1. So I put the number 5 on the write port, I set the write address to 1, and I press the button, and that will have written 5 to register 1. And so now let's say I want to look at these registers. Let's say I want to look at register 0 on port A. Then I'll set read address A to 0, and as you can see, that 6 comes up. The 6 that is stored in register 0 now comes out on port A. Likewise, if I want to see what was in register 1, then I would set read address B to 1, and what do you know it, the 5 that we just stored in register 1 shows up in port B. This should give you a good enough idea on how the register file works, or at least how it functions. But if you want to know more about it, well, this uses multiplexers and decoders, which come from Logical Redstone Reloaded number 6. And it also uses registers, of course. It's a register file, and those come from Logical Redstone Reloaded 7. All right, next I'll be going over how the ALU and the register file can work together to carry out these program instructions. So as you can see, I've wired up that read port A of the register file to input A of the ALU. I've wired up read port B of the register file to input B of the ALU, and then I've wired up the result of the ALU to go into the write port of the register file. So the instruction I'll be going over in this example is add 201, which is the one from the video, but I'll be doing it in more detail. So first of all, To figure out which numbers in that instruction go where, what you do is you look at the instruction set and you see that the destination address goes first, and then read address A, and then read address B. So let's start with the read addresses. In this case, the read address of A is 0 and the read address B is 1. So what this will do is it'll tell the read ports to take the value from register 0 and the value from register 1. And so the value of register 0 goes into the ALU from input A, and the value of register 1 goes out on read port B and goes into the ALU on input B. The add will tell you that the opcode is 6, and this will obviously make the ALU add the two numbers together and output the result. And the destination address, lastly, is 2. And what this will do, once I press this button, is it will save whatever result came out of the ALU into register 2. So in short, what this did is it took the value of register 0, it took the value of register 1, it added them together, and then it stored the result in register 2. And as you can see, I put lamps here to make it a little easier to see. The value of register 0, as you can see here, is 6. And the value of register 1, as you can see here, is 5. So when we look at register 2, we should see 11, and we do. So that's cool. Another instruction I'll be going over, just one more, is LDI 725. And if you look at the instruction set, you could probably tell what this is already supposed to do. Basically what it does is it'll take the number 25 and it'll put it into register 7. So first we'll cover the opcode. LDI is 10, so that'll just tell the ALU to take whatever's on the immediate output and pass it straight through. Obviously we have the 25 here, which, if I'm not mistaken, is that. And then the destination address is 7. And so what this will do is it'll store that number 25 into register 7. And I just put some lamps here again to make it easier to see, and you can see that the number 25 does appear on register 7. Okay, so next I'll be going over the instruction ROM, which, as I said, holds all the code in the program. So because we're working with Redstone signals that can only be on and off, what we have to do is program in machine code, which is a lot different than the kind of code you might have been used to programming with if you're, just a regular coder. You can't write things like printf hello world. You can't do any of that because you're dealing with literal ones and zeros. Like, you have to write your programs in ones and zeros. And so each line of code right here is represented by like this vertical redstone line. And every time you see a repeater here, it's a 1. And every time you see a blank space here, that's a 0. So each line of code here has a number. And the way you access these numbers is by using this address here at the bottom. So let's say I wanted to access line 10 of the code. Then this would be set to 10. And as you can see, if I go over to where line 10 is, you can see that this line turns on, whereas all these other lines turn off. And whatever value is stored here in line 10 gets put on this output right here. And so this output will then just get like split up and delivered to all the other components of the computer. So this is a decoder here on the bottom and an encoder on the top, and both of those come from Logical Redstone Reloaded number 6. So the program counter used in this design was basically taken straight out of a Logical we'll just go with that. Logical Redstone Loaded number 8. And so what you can see here is that when I press the count button on this thing, what it does is just increments to the next number. So it goes from 4 to 5 to 6 and so on. But the load button, when I press the load button, whatever is here, the program counter takes this and passes it straight through. And this is what allows you to make loops in your programs. So here are the 3 instructions that allow you to put loops in your programs. And they're pretty similar in that they take an address that you are supposed to jump to. But the way they're different is that this one here is unconditional, and these two here are conditional. And so what that means, for example, this unconditional one, if I had something like jump 20, it would always go to line 20 when it came across this instruction, no matter what. But for example, jump if 0, this one's conditional. And what this does is it relies on the 0 flag that comes out of the ALU. And only if this 0 flag is on does the jump if 0 instruction actually move to move to the line specified. Otherwise, it just continues on like normal. And jump if negative is sort of similar, except instead of using the 0 flag here, it uses the most significant bit of the ALU result. And without going into too much detail, you can treat the number that comes out of here as negative if this bit is on. So you can see here that I've added this logic in front of the program counter. And what this does is it checks the values of the flags here, and it checks the value of the opcode, and then it powers either the count or the load inputs to the program counter, depending on what it's supposed to do. Now, note that not every single ALU operation will update the flags though, because they only update if the letter corresponding to the flag is in here. So for example, the bitwise AND operation I talked about earlier, it would update the 0 flag, but it wouldn't update the negative flag. Whatever value the negative flag had would just remain the same. And lastly, I just added this reset wiring on the front. And what this does is it just resets the program counter back to 0 so you can restart the program. So here's the full prototype, which it puts itself together. You can see here that we have the clock signal that's going to the registers and also going to the program counter. So that's how that timing works. And you can also see here, here's the 7-segment display, and you can see there's a 6 on it. Now there's a 7, now there's an 8, now there's a 9. And so there's a 10, 9, 8, 7. So yeah, you can see it's running that program I showed in the actual video. And I'm actually going to be explaining how that works here. So the way this program works, this is a count up and count down program. It has 3 registers here. And the way we start out is we initialize them by putting a 0 into register 0, and we put a 10 into register 1. And register 0 is, in the future is going to be the number that actually counts up to 10 and then counts back down to 0 and so on and so forth. Register 1, this 10 in register 1 actually stays here forever. It doesn't really need to change. But now that we've done that, we've done this, so we can move on to our first loop here. So what we do, we'll increment register 0, we'll make it a 1, and then we subtract register 1 from register 0 and store the result in register 2. In this case, we get -9, and the reason why we do this is because, we can't compare our number with 10 directly. There's no such instruction as jump if 10, at least on my processor. So what we're doing instead is we're subtracting this value here, we're subtracting 10 from it, and we're waiting for this result to be 0. And then that's how we know that this register here has hit 10. So since, in this case, we obviously don't have a 0, so this instruction here is ignored. It doesn't jump to 6, instead it jumps to 2, and it repeats again. So this ends up being 2, and this ends up being -8. When you subtract 10 from 2, you get -8. And this obviously is still not 0. So, instead of going to the second loop here, it'll just go back and do the first loop again. And obviously I'm not going to do every step, but eventually register 0 will hit 10. And so when we do the subtraction, we get 0. And because of that, now we know that we've reached 10. So what it's going to do is it's going to jump to the second loop. And so it's going to start counting down. So we'll start by decrementing register 0. So we go from 10 down to 9. And Notice how there's no subtraction here, and this is because we're actually waiting for the value of register 0 to become 0. And because we can actually compare with 0 directly, what we can do is we don't have to worry about subtracting it. We can just keep decrementing this register over and over again until we reach 0. So, in this case, it's 8, not 0 yet. So we're going to go back to here, and it's just going to keep doing this loop over and over again until the value of register 0 eventually reaches 0. And then it triggers this jump if 0. Well, it is 0 now. So now what we do is we, then this triggers here, and it goes to not there. And so it goes to register, goes to line 2. And so now we're back in that first loop, and we can count up. So yeah, that's basically how that program works. Pretty simple. Okay, so this is the RAM, random access memory. At least I think this is what this is classified as. I'm not 100% sure that this would qualify as RAM, but that's not really my wheelhouse. I like using that word. But the way the RAM works is that it's sort of like the register file, but the register file where you could do things like read from port, register 2 and read from register 1 and write to register 0, like all in the same instruction. You can't do that here. You notice it only has one address at the bottom, and this doubles as a write and a read address. So let's say I wanted to put the number 2 into register 5, address 5 of this RAM. So I would set the write port to 2, set the address to 5, push that button. And since I'm also reading from address 5, as you can see by that, you'll notice that that number 2 came out on the output here, the read port. But if I were to switch this read port to look at a different address, such as address 6, then you'll now notice that because I'm looking at a different address, the 2 that we put in there isn't going to show up. Now you might have noticed about this RAM is that this piece is sort of missing from it, from the beginning and the end. And that is where the inputs and outputs, meaning like the actual system, like the computer's peripherals, are going to go. You can see what addresses get which peripherals by looking at the table on the right side of the instruction set. So because this component is like the register file, you wouldn't be surprised to figure out that this also has multiplexers and decoders, which are found in Logical Redstone Reloaded 6 and Logical and registers, which are found in Logical Redstone Reloaded 7. Alright, so before I get into the actual inputs and outputs themselves, I first need to introduce you to a concept called BCD, or binary coded decimal. So I've already explained what binary is. It's a system of numbers where each digit gets 2 times more significant than the last one. And so when you want to represent a number 231 in binary, this is what it would be. However, binary coded decimal, or BCD, is, it is decimal in the sense that, there's a hundreds place, a tens place, and a ones place. But each one of these places, each decimal digit is decomposed into a 4-bit binary number, which expresses that digit. So for example, I'm doing 231 here. So the hundreds place, you have 0010, which is 2. You have 0011, which is 3 for the tens place. And you have 0001, which is 1 for the ones place. So if you wanted to write 231 in BCD, binary coded decimal, you'd write 0010, 0011, 0001. And so this is a way we can sort of make decimal input and output available to the user, even though the computer has to specifically work with binary numbers. All right, so going into address 1, this is the BCD to binary converter, or you could call it the numeric input. But basically what this does, it lets you write one digit at a time using this binary coded decimal system and enter it, and it'll show up on the output. So for example, what we're gonna do is let's make 42. So we have a 4 here. So that's how you make the 4 in binary. We're gonna hit enter, and then we're gonna make 2 in binary, and then we're gonna hit enter again. And you should notice that we get this number, which is 42 in binary. So we're gonna set that to 0. We're gonna clear it again, and let's do another one, just make 69. So here we have a 6 because it's 4 and 2, enter, and then I'm gonna make a 9, which is 8 and 1, and then I'm gonna hit enter again. And you can see we have a 69 on the output in binary. This design is pretty much taken from episode 11 of the old logical Redstone series. All right, so here is the button input, and I made this myself. It's literally just wiring, so it's hopefully I wouldn't need a tutorial to figure this out. But anyway, this goes into RAM address 1, and it's got its up, down, left, right. It's got like its Y, X, BA, like it's an Xbox controller sort of thing. And then all these inputs here, they sort of get like turned into a single 8-bit number, and that's what gets fed into the RAM. And the way that we can test for specific inputs is by using a technique called bit masking, which I'll explain now. I did 4 takes on this and then realized I was recording my Minecraft instead of the monitor. Let's go again. So let's say we had this input here, right? This was the 8-bit number that comes out of that controller, and we wanted to test for A being pressed. Now, a human would just be able to look at this bit right here and say, well, duh, obviously A is pressed, its corresponding bit is 1. But a computer can't just look at an individual bit with a single instruction like that. It can only look at the whole number. But what we can do is we can use the bit masking to force certain bits to be off, so we can get rid of all these, and we can only focus on this one, and what you end up getting is a number that's either 0 or non-zero. And while we do have an instruction that can check if something's 0, we have jump if 0. So the example test for A, what we would do is we will write our input like this. This is our input. And to make our bitwise mask, we put zeros where we don't care about. So for all these, because we don't care about them, we put zeros here. And for this one, because we do care about it, this is the one we're testing for, we put a 1 here. And numbers like these, just any arbitrary number, we can program this and we can load it directly into a register with that load immediate function. So that's where that comes in handy as well, if you were wondering. That is a use case of that load immediate function. But when we take this bitwise AND, remember that in these columns here, both bits have to be 1 in order for the corresponding bit of the result to be 1. So these are all going to be 0, of course. And because these are both 1 in this last column corresponding to A, well, this bit here ends up being 1. And when we use that jump if 0 instruction, we find that this is not 0. And so now we know that A is on. It's being pressed. The next example is X, and I will copy this input again. This is X right here. That's the bit that corresponds to it. And the way we will make our bit mask here is by putting a 1 where we do care about it, and a 0 for all those inputs we don't care about. And when we do the result of this bitwise AND, you will find that it is all zeros. And because of that, now we know that X is off, or not pressed. Now, you aren't limited to just testing for specific inputs, like one input at a time. What you can do is also here test for any direction. So one of my programs actually tests for any of these being held. And in that case, what the bitwise mask you would use would be this. 1s at the start to correspond with these, and 0s to correspond with these because we don't care about them. Now, this process of, isolating certain bits by forcing the others to be off isn't the only use of bit masking. You can also use the OR operations to force certain bits to be on or 1, or you can also use the XOR operations to toggle certain bits. But this process in particular with the bitwise AND is the one that is most commonly used in the programs I'm writing for the Redstone computer. All right, enough about that boring bit masking stuff. Let's talk about something fun like gambling. This is a random number generator that generates a random number when you press this button, and it's hooked up to the clock, so it's every clock cycle. But yeah, so as you can see, this number here is 62, and this number here is whatever that is, and so on and so forth. But yeah, basically yeah, that's 42. But yeah, the way this works, basically, that's a 5, that's easy. The way this works is it uses these dispensers, which spit out a random item, and these shulker boxes which each have like a different number of items in it, and they correspond to different signal strengths. So this contraption here will output a certain signal strength on that comparator, and then that signal strength is converted to binary using this signal strength to binary converter. Did you think it would be called something else? The top one is basically the same. So when you have this bottom one generating a random number and the top one generating a random number, you could just sort of just put the two together, and that's what I did. This generates a random number from 0 to 63. So actually, this is one of the few parts that didn't come from the Logical Redstone series. So this here came from a video by Mumbo Jumbo, this part right here, this Redstone randomizer with the shulker boxes and whatnot. And then the signal strength to binary converter came from another video by MattBat about the binary and hexadecimal Redstone systems. So I'll definitely be linking to those too, as well as that Logical Redstone series. All right, so this is binary to BCD output. This goes on RAM address 12, and this is quite a big thing. So the way this works is pretty simple. You enter a number in binary here. Let's do 146, which is that. And then you see on the output that you indeed do get 146. So the way this works, it uses this big ass thing right here to convert the binary number to a BCD number, as I explained earlier. And then each of these digits, for example, this is the hundreds place, this is the, my bad, I got that reversed. This is the ones place, this is the tens place, this is the hundreds place. So each of these digits gets sent to its own 7-segment display, which you can see here. So the binary to BCD converter, this part, that can be found in episode 10 of the old Logical Redstone series. It's specifically the combinational one, not the sequential one. And this one here is the 7-segment display is, again, from Logical Redstone Reloaded 9. So this is the alphanumeric display, and it's the one that can show both letters and numbers. So the way this works is we have actually two inputs here. We have the position, which is hooked up to address 11, and the character system, which gets address 10. So the way the position works is you can set this to be any value from 0 to 7. And so you'll see on the leftmost display gets a position of 1. The next one gets a position of 2, so on and so forth. The rightmost display will get a position of 6. If you set the position to 0, it will not print on any of the screens. And if you set the position to 7, it will print on all of the screens at once, which is useful if you want to clear it. And the way the character system works is this input can be anywhere from 0 to 63. And so if this number here is anywhere from 0 to 9, it'll print out that corresponding digit. So, 0 through 9. If this is 10 through 35, those actually get assigned to characters A through Z. So 10 would be A, 11 would be B, 12 would be C, so on and so forth. 35 is Z. And if you put anything else, so in this case 36 or greater, you end up getting a blank space. So, and also this comes from RAM address 10. So let's start with, let's say I wanted to print something like high. Well, H would be 17, so that, and then I wanted to print it on position 1, so I would do this, and as you can see, it prints the H here, and now let's do the I. Well, the I ends up being like indexed at 18, and we'll print it on position 2, and you can see here that there's a little I next to it, and so we can clear the screen. Again, we set it to any number that's not between 0 and 35, so I like to just do 48, and let's print it on all displays here, and you can see now we go to the other side and it is clear. Alright, so here's one big disclaimer you're going to need to know if you want to try and program this display on your own, and that is that this display, the way I made it, it's continually updated, or that's just the only term I can think to describe it. And what this means is that after every clock cycle or every instruction, what it's going to do is it's going to update this display based on what's stored at the character and position. And this might seem obvious, but this can lead to some unintended behavior if you're not careful programming it. So we're going to use the example of printing high again. So let's assume that we're basically right here, right? And character H, so that would be that. The position would be 1. And oh yeah, this is RAM address 10. This is RAM address 11 if you just want to be specific about it. So what this will do, obviously, it will print the H in slot 1. And this is good and all, but if you change the character to I, what you would do is, well, instruction just happened, so now it's going to try and copy this data over, which is print an I in position 1, and instead of printing an H, it'll do this. And then when you change the position to 2, it'll do that. And that makes E, that doesn't make I, it's 2 I's, it's obviously wrong. What you could do to try and remedy this is you could swap these two lines around here. You could swap those. So let's go back to printing H at position 1. You could swap those. So now we're printing H at position 2, but then this will print an H here instead of an I here, because it'll print this data instead. And only when after we change the character to I will it actually show up as high. So this would work, but it's like a little janky because it'll show HH before it shows high. And that's not quite up to my standards. But the correct way to do this, as you see here, is to have this line in between. This is super important. So remember when I said earlier that position 0 will not, like if you have the position set to 0, it'll not print anything anywhere. And that's why what I've represented here with this little crossed off blocks. It doesn't correspond to any of these 6 slots in the alphanumeric display. So let's go back to this line here where we had printed H at position 1 like this. Once we change the position to 0, what's going to happen is, well, it's going to try and print H at position 0, but it can't because that doesn't really correspond to any spot on the display. So we can now change the character to I. And this will try and it'll say print an I at position 0, but again, it doesn't show up anywhere, so we're good. And then it'll change the position to 2, and this goes straight from saying H to saying hi. So this is what we want. So in general, whenever you're switching between two characters, printing characters in two separate slots, what you want to do is you want to have this line in the middle that says to change the position to 0, and that makes it not update anything while you change the character. Now you're going to be seeing a lot of code sections that look like this in the Hello World program, which I should be explaining later. Alright, so in this next section with the screen, I'm going to be explaining the version of the screen that's actually in Logical Redstone Reloaded. And then I'll be showing you what I modified to make it a little more friendly for a Redstone computer to use. So first, this screen right here. Each pixel right here is made up of this square of 2 by 2 redstone lamps. So this square right here, this is 1 pixel. And so the x-coordinate starts here at 0 and it increases, goes right as it increases. The y-coordinate, as that increases, you go up. So this point would be 0, 0, and then this pixel all the way up here would be 7, 7. This would be 7, 0, and so on. So as you can see here, this is an x-coordinate, this is a y-coordinate, and right now it's just set to 1, 3. The data here, this determines if whatever you're about to do here will be with like whether or not you want to make things on or you want to turn pixels off. So there's 2 buttons here, plot pixel and plot all pixels. When I hit plot pixel at these coordinates and data is on, that's important, we should expect to see a pixel about there. So up there, yeah, right there. So and I'll show you plot all pixels, and that just, does exactly what you think it would do. And if I turn this off, plot a point there. Now I can erase a point, and I can like change these coordinates around to erase another point somewhere that's at 5, 3. And then if I want to clear the whole screen, I can do that too. So first up, we have a switch that either enables or disables it. So that will, so when the switch is 1, any change you try and make to it won't go through. This switch switches between plotting pixels and plotting all pixels, which was previously shown with those 2 buttons. And this switch here is basically the same as the data switch. It's just either whether or not you want to plot something that's on or you want to plot something that's off. And then this button here, this is how you'd actually trigger it. So let's say I want to make that point at 1, 3 again. 1, 3. So I would have to do that. I have this Arithmetic Display enabled. I'm going to plot 1 pixel, and I'm going to plot that pixel to be on. I'm going to press this button, and then it'll come up. And so filling out the whole screen would be done by using plot all instead of plot 1. And then erasing a point would be done with by switching this to be off. I won't bother with the coordinates this time. And then plot all with an off pixel will erase the whole screen. And just for the sake of completeness, I'll show you the disable function too. So, normally what this did before when I had this configuration is it plotted a pixel at 1, 3. But if I have this enabled, you can see it just won't do that, So this here, this is a 3-bit number that we can put in. And that ends up being, that's in RAM 15, the scream operation. This one here is the x-coordinate, and that's in RAM address 13. This is the y-coordinate, it's in RAM address 14. Okay, so like the alphanumeric display, there's a disclaimer about programming the screen too, and that it's also, in the sense that it's also continually updated. So what this means is it will like try and plot whatever data is here every single clock cycle. And so let's say you wanted to plot a point at 0, 1, and then you wanted to plot a point at 3, 3. Assume you already had the operation that plots a point, right? So you would think, imagine yourself here, right? you would think the way to do it would be as simple as that, right? Where you had this pixel plotted, and now you just want to change x to 3 and you want to change y to 3 and you want to try and get this plotted too, right? Unfortunately, this won't work because, well, when you change the x to 3, after you change the x to 3, it'll still plot all this stuff. And so what it'll do is it'll actually plot at 3, 1, which is here. And you don't want that. And then it'll change y to 3 and it'll do this. So you see it plotted an extra point and we don't want that there. So the way to fix that is via that operation there that does nothing. If you recall, you have like 3 bits in the number. The first bit is 0 for enabled and 1 for disabled. So the operation to do nothing in this case, that would be 4, but it could be 4, 5, 6, 7, any number. I just chose 4. So let's say you had your pixel plotted at 1, 1. You were here, right? So you have 0, you have 1. Sorry, I said 0, 1. So now you want so let's change the operation to do nothing. And so now this lets us safely make our changes without actually affecting what's on the graph. So you can see I could change x to 3 and it's fine because it's set to do nothing, so it won't try and print anywhere. Same thing with this deal. Now we have the correct coordinates and the screen is not, the operation is still doing nothing, so it won't print there. And now if we change the operation to plot 1 pixel, now all the data is correct. So now it plots here. So if you're going to plot 2 points like this, then what you have to do is you're going to have to change the operation to do nothing, make your changes, and then set it to plot 1 pixel. Now, what you can do instead, let's say you wanted to plot like an L shape, like that, you could easily just have it plotting, here. You could have it plot here and then change the y coordinate, then change the x coordinate without, like if you want this artifact here, you can just change the coordinates directly without changing the operation. Like that'll do if you want to print something like that. But if you want to print stuff that's diagonally, like if you want to plot points that are diagonal from each other, like the example here and here, then you're going to need to do this. And you'll be seeing this in the program with the smiley face on the screen, where I have to plot a point like, this and like this, I have to plot them diagonally like that. Now I will admit that this whole like disabling operation was sort of added at the last minute, so I'm sure there's a better way to do it. Anyone who wants to, improve the screen so that programming it becomes like easier, yeah, be my guest. It won't be me though, I'll tell you that. I am ready to not be doing this project. It's cool, but like, it's been pretty tough, man. It's been like a lot. Oh yeah, and I guess that's the end of the explanation about like the computer itself. So I hope you enjoyed. Who's enjoying this? I hope you understood this well enough. And if you didn't, then again, feel free to make a comment, ask for help, clarify, and I'll do my best to clear things up. All right, so right now I'll explain the Fibonacci program, which was like the first milestone. So we have 3 registers here that we're dealing with. What is going on with my drawing tablet, dude? What is the problem? Okay. All right. But anyway, yeah, reg 0 acts as the less recent term. And then reg 1 acts as the more recent term. And then reg 7 is like the sum sort of, or this is like the Fibonacci sequence that actually like gets displayed is here, like the one that the register I was looking at with the lamps in the video, that's this one. So we're gonna start out by taking the, we're gonna put clear this, clear that, right? So show that 0 first, and then show the 1, and also put it in here. And then now what we're gonna do is we're gonna actually like add them. So we're on step 4 now. We're just gonna add them, and then here's the thing though, because we're working with numbers that are 8-bit, we only have this range here, which means that we want to make sure that our number doesn't overflow and get higher than 256. So basically what we got to do is these two lines here, 5 and 6, those are for overflow detection. So what we're going to do, if we're adding these two numbers up, I made that mistake in a previous take too, or whatever, I'll just roll with it. So we take this 0 plus 1, we add a 1. And the thing is, we need to make sure that it doesn't overflow. Now, how can we tell if this overflows? If this number ends up being less than the term in the sum, then we know that, because, right, if we have 1 plus 2 equals 3, well, it's impossible for the result of 1 plus 2 to be less than 2, right? We can't have 1 plus 2 equals something less than 2. That's impossible. So we take the most recent term here, this 1 in this case, and then we subtract that. And then in this case, we want to make sure, we want to see if the number's negative, then we know it overflowed right here. If the number's negative, we know it overflowed, but it didn't overflow. It's not negative, so we're just going to keep going. So then it moves the 1 and the 1 to here, and then it puts a 2 there because it adds them. And then we do 2 minus 1, which is 1 greater than 0, which is means that, of course, it hasn't overflowed yet. So we keep going, 1 plus 2 equals 3. So, and 3 minus 2 is, obviously not negative. So if we haven't overflowed yet, this keeps going on and on until you eventually get like 144, 233, and then when you try and add these up, right, you would get 377. But the problem is that this is obviously too big for our computer to handle. So it gets turned into 377 modulo 256, which is 121. And when you do the 121 minus the 233, well, that ends up being less than 0. So this condition here ends up being true. And so that means that we go back to the start like that. And then I could have made this program just stop when the overflow happened. I chose to make it go over again, just a choice. But yeah, that's how that program works. It's pretty simple. Oh, and then by the way, this one actually doesn't have a this is the one that doesn't show stuff on a screen. It just shows stuff in like register 7, so you have to put lamps on it. But I do have one that uses the screen. You can just see here that there's a couple extra instructions here that display the numbers on that numeric display. Okay, here's the multiplier. Now, most of it is like pretty self-explanatory. I think I commented it pretty decently enough. I just want to mention a couple major like high-level things about how it works. So the way you're testing for that button input, again, you see here, these are the button masks, because again, the input goes like this. Yeah, because the format of the button input is like this, you can clearly see that this bit mask is testing for input A, and this bit mask is testing for input B. And if you want to know why, I can put the timestamp up to take you back to that section about bit masking. So yeah, basically what this does is here it loads the input. Oh yeah, I should probably say how this program actually ends up being used, right? So you put your first number in like 3, and then you press A, and then you put your next number in like 5, and then you press B, and then this is sort of like the times, and then this is sort of like the equals, and you end up getting your result on the screen. So as you can see here, it's just it's taking your input, and then it's checking to see if the button A is pressed, and then if it's not, it goes back to here. Same thing here, load the input, check if B is pressed, and if it's not, go back. Once everything's done, then it basically just adds the number to itself over and over again until it reaches the product. Like it literally just does 3 plus 3 plus 3 plus 3 plus 3. There are better ways of doing this, but I would just happen to be lazy when I was making this program. And then yeah, it shows the product up, and then it just goes into an infinite loop to stop itself. And yeah, that's about it. Okay, so the last thing I want to go over is the Hello World program, and again, I think most of it is pretty self-explanatory, but I want to go over one thing real quick. Just note here, you have these letters in these groups of like 4. This is the code for printing the word, and you can see here that what this does is first it puts a 0 in the position to stop the screen from printing. Then it takes the first letter, like it takes the letter and then sends it to the alphanumeric display. And then lastly, it sends the position you want to actually print it at the alphanumeric display. And that's how you prevent the screen from like behaving buggily, if that's even a word. Stop the screen from behaving weirdly when you try and print letters on it. And if you want to know more about that, if you missed that section, I'll just timestamp it up right now. But yeah, that's the Hello World program. But yeah, that's basically about all I want to say about the Hello World program. Again, if you have questions, you could put in the comments. All right, so I'll show you this program. This is like the last program that I made. It's just pretty cool. It's like a calculator program. But basically, what this does is up is addition, left is subtraction, right is multiplication, down is division. So what you do is you use it like you would a normal calculator. So first you enter in your number, right? So as you can see here, I have 1, which means I'm entering the first operand. So we're going to clear this, and let's just enter like 8, right? Let's do 8 times 5. So I'm going to hit 8, I'm going to hit enter, and as you can see here, there's an 8. So now I'm gonna multiply it. So I'm going to press this right lever. You can see there's going to be a 2 on is going to come up, yep, and then I'm going to clear it, and then put in 5, and then enter it, and you can see then there will be a 5 up, and then then I'm going to go actually compute the result, and then it'll take a little bit of a while, but you should see a 40 come up in like 30 seconds. Okay, there we go. That was a little quicker than I expected, but yeah, you can see a 40 comes up. Let's try division too. Let's do like 72 divided by 11. Yeah, we'll do that. All right, so we'll clear. Oh yeah, first of all, what you have to do is you actually have to reset the program. So we'll do that, and then we'll do 7, and then 2, and then it should come up there. Yep, 72. So then let's divide, and then see there's should be a 2 coming up there. Yep. Okay, we'll do 11. All right, and then let's compute the answer. It just switches to 0 when it's displaying when it's like busy calculating something. So yeah, I just had to give it that behavior because it has to switch to something. So I just figured let's just make it display 0 while it's busy. But yeah, you can see 6 remainder 6. The remainder just gets shoved here. But yeah, pretty cool. So RecRap built a calculator in Survival Minecraft. Yeah, but so did I, except my calculator is just a lot shittier because it can't deal with numbers above 128. But hey, I guess the trade-off is you get a cool smiley. Look at that. All right, guys. So now I'm gonna show you how to program the Redstone computer. So first of all, you actually have to make your program, and this one is a pretty simple one. I'm just going to make some example one. It's going to print funny number to the screen. So we'll do that. First thing you need to do when you're making your program, you got to have a line number. So you have to have this line number here, like that. Then you have to have your instruction. And then if you want to put a comment, you do 2 slashes before it. And then, and then put your comment. And another thing you can do is, in order to make this, look better, you can go to language. You go into user-defined language. This is for Notepad++. You open user-defined language Notepad, and then there's this file I'm going to give you, redstoneComputer.xml. You just put it in there. You might have to restart it, but basically then you can hit language and you can hit Redstone Computer, and then it'll just it'll just format things nice and cool. Anyway, I'm going to make the next part of the program, which just puts the funny number onto the screen. And then you can even make comments on lines that don't have the code on them. So like this program prints funny number, right? So you can do that. So here's our program. We're just gonna save that, and then what you're gonna do is you're gonna use this Python script here. I know in the video I said I made it with C++, but I have one here. I made it again, and this one's just better. But anyway, yeah. So you enter your file name like that, and then you can see it converts the program to machine code. And if you were to open this, and you can see here that it got converted from its assembly instructions to just the ones and zeros. So the way you do this, you actually put this in the computer in Minecraft, is you're going to select this, you're going to go to the instruction ROM, you're going to select this bottom one here, you're going to select the top. This assumes you have world edit, so replace repeater air expand 1 stack 31, and then to clear the other side you would just do the same thing. But yeah, so then we're going to actually write the program into the instruction ROM, and the way you do this is you just put a repeater when there's a 1, leave a space blank when there's a 0, so like 1 0 1 0 0 0 0 0 1 0 0 0 1 0 1, and then for line number 1, again, make sure you're putting them on the right in the line numbers. 1 1 1 0 0. Okay, so then in order to actually run your program, you do is if you have the carpet mod, which you should have, tick rate 1000 to speed things up, and then you press the button, and as you can see, did I do something wrong? Hold on. Oh, it's I know why. It's because I was in debug mode. So yeah, basically the thing about the debug mode, if you have this switch off like this, it's disconnected from the clock signal, and you can use the button to go through it. But we don't want to do that. So let's just we take the switch up, and then as you can see, it's gonna run the program, and it's gonna print the funny number on the screen. But yeah, if your program isn't working, make sure this is, first of all, actually make sure your code is right, but also make sure this debug switch is set to normal. So here's another debug feature that you can use, right? So you go into debug mode, and then let's say you want to specifically go to a specific line, like let's say something ran incorrectly and you changed a part of the code and you want to go back to make sure it runs correctly. We could do over here next to the program counter. I have this part where you can force 1 and force 0, you can force it to be a certain number. So let's say you want to change it to 49. You want to see, you have some code written after line 49 that you change, and you want to see if that works correctly without running the rest of the program. So what you do, you'll set 1 1, and then you'll put the zeros here, so it'll look like that, and then you load that into the program counter, and then what you got to do is oh well, you can actually get rid of these switches now. Confirm that the program counter is displaying a 49, and then you would go here and press the button like this. And then if we go over to the program counter, or over to the instruction ROM, we should see that it's on line 49 or 50, whatever the fuck, I don't care. Also, is it supplementary or supplemental? Can some grammar nerd in the comments please help me out? Thank you. Alright, so now I'm just going to go into a little bit of detail on a real hardware design, or at least how it's done in my classes so far. So this is an FPGA board, and what this does is it basically allows you to design a circuit, the circuit gets stored on this board without you actually having to go in and wire the things together, which is really cool. And I don't really know how it works, but I'm not complaining because I'd rather not actually wire transistors together to make hardware. That sounds like hell. But yeah, while I was making the computer in Minecraft, I also was wondering how long it would take to make the computer outside of Minecraft and implement it on this board. So I did just that. I have this board, but I don't have the screen, obviously, so I can't do that, but I can do the alphanumeric display, the numeric display using the 7 segment here, and pretty much everything else remains unchanged. So yeah, I don't have the project files because I unfortunately don't. I had to reinstall Windows on this computer, so I unfortunately don't have. Yeah, I lost the project files, so I can't actually get the computer back on the basis board. But I did have it on once there. Just trust me, guys. It was cool. But anyway, yeah, I have footage. I have footage of me making it, of encoding. I was gonna use this in like the regular video, like the main video, but then well, I decided not to when I took the direction and when I realized, oh, this would just not be related enough to what I was actually doing in the video. But yeah, you can see here, I'm just coding. I have all these different files representing, like, here's the ALU, the instruction ROM, the register file. And then you can see, like, later on, it took 6 hours for me to make the computer outside of Minecraft using VHDL. And I should probably explain what a hardware description language is now. So hardware description languages, that's how you actually program this FPGA. And instead of a regular programming language where you list out a bunch of steps that the computer has to do, you're instead like putting down components and you're sort of describing the layout of the circuit, which is, you know, it's pretty cool. It's sort of a nice alternate way of thinking about things. But the cool thing about VHDL, which is the hardware description language that I, know, is that like when you're programming something in like VHDL, you don't have to use, you don't have to always think about the underlying digital logic. Like you could see here, like I have if statements there, like behavioral statements and stuff like that. You're not always thinking about where each logic gate goes. And that's, that's pretty cool because the less thinking you have to do, the better. You can even use like arithmetic operators like plus signs, multiplication signs, and the the synthesizer will just sort of turn that into digital logic for you. So basically, what I'm getting at here with this section, the theme of this section is that while Redstone is very cool, it's also really tedious to design things with Redstone compared to designing it using a hardware description language. So if you happen to be interested in like hardware design or like programming in general, then don't let the complexities of Redstone like turn you off, because this stuff's actually just like a lot easier than it looks. At least a lot easier for me than it looks in my video. I can at least guarantee that. All right, let's talk about the making of the video now. This is going to be the huge ramble section, so bear with me. It all started on this one day when I received a comment by user StuffAndThings that said, is there anything in Minecraft that you can't speedrun? And I thought about it and I was like, well, I mean, I can't build like a giant redstone computer in Minecraft like some people could. And then I thought about it for like a couple more seconds and then I was like, wait a second. I'm in hardware design classes where they teach me how a computer works. I can totally build a computer out of redstone if I really wanted to. So yeah, there is a good chance that even if I didn't receive that comment, I still would have gotten the idea to make the video just because of how much I was into that hardware design stuff and how much I liked those hardware design classes that I was taking. But yeah, it's kind of interesting to think that like that was sort of the catalyst to make the video happen. So once I realized I could make this computer thing, I got locked in. I had a creative world where I was testing out like various different designs, experimenting with the redstone gates, making my own things. I don't have the world, unfortunately, but I do have some screenshots from it, and I'll show you those. And as you can see, like some of the designs weren't optimal. Like you can see in this picture on the top, there's my design for a 4-bit adder, and then on the bottom there's like the optimal design for a 4-bit adder. And the reason I was building these things like so sloppily is because, well, I had sort of a different mindset where I wanted to try and see if I can build the components by myself without any help before I went to looking them up online to seeing how they worked. and how they were properly implemented in Redstone. And the reason I wanted to do that was because I sort of wanted to like prove that I could build the Redstone computer by myself with no help if I really wanted to. So once I started, I had got a couple components down. I started drawing some diagrams, and then guess what happened? I got distracted. I started playing like SpongeBob instead. I started playing a bunch of different Minecraft CTM maps. I went into DUTM. I went into Pack and Roll Remix. I even had a little bit of a Wii Sports Resort phase. And so obviously it wasn't really until like the new year rolled around, 2024, when I started thinking like, wait, like I want to get this project done at some point. I should probably like start really locking in and start actually focusing on it. And that's what I did. And so obviously, as you know, throughout like from late January up until November, there was no uploads on the main channel. And that's because I was working on that goddamn Redstone computer project. I took some breaks to, speedrun some maps to keep me sane, but those were all got offloaded onto the second channel. But so yeah, it took from January up until like early March is when I spent all that time planning out the computer, drawing those diagrams, building the computer in creative mode, programming and stuff. And then from early March to late May was spent doing the survival challenge. Now, the thing is, even though I spent less hours in the survival challenge than I did in the creative world, motivation sort of started to become a problem in those later months of the challenge, because like obviously like it makes sense, right? Like I naturally am going to be less motivated to go on Minecraft if all I'm going to do is just click on an armor stand in the raid farm over and over again, or do void trading over and over again, or just mindlessly copy and place the same blocks over again and debug Redstone and have to deal with that. I mean, as JR5000 put it, I need a break too if I was spending hours debugging Redstone. And then I finished it after the semester ended in like late May, and then I edited the video, and oh boy, I have so much to say about editing the video. So in June, right? June was sort of like when I had a lot of motivation to edit it, but I was like more I was too perfectionistic. That was my problem. So I really wanted to go into a lot of detail about every single part of the story so far. And I wanted to, I was under the assumption that I wouldn't be making a supplementary video. So I wanted to like explain all those components in detail, like the ALU, the register file, instruction ROM, blah, 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 whatever. And I had these beautiful edited segments out with examples, with diagrams, with all these cool isometric renders, all that stuff. I'll link that section in the description because it's definitely worth watching if you want to know how those things work. Definitely better than anything in this supplementary video. Yeah, I'll put that down there. But I basically made that, and then I showed people it, and I showed my early access team it, and I came to the conclusion. I'll get into how I came into that conclusion later, but basically I realized like not only am I going to take way too long to finish the video if I keep going at this level of detail, it's going to be super long. It would be like a 2-hour video, where like 1 hour of this 2-hour video was spent not even in the survival world. So like it would be pretty bad, right? It would be a pretty boring video. Like it would be, people would be snoozing, they'd be clicking off in the first 5 minutes. Like I wouldn't get any sort of a viewer base whatsoever. So then I really had to, pivot, shift the focus of the video into the survival challenge. And so, I mean, I basically ended up scrapping that 11-minute segment, basically almost not including anything from it. And because of that, that's when I started, when the burnout really hit. Also, I was on a 2-week vacation. So, I mean, obviously I'm not going to be in Europe like editing my video, even if I had the time. Like that's just not something you want to be doing, right? So so yeah, I didn't really get as much time during the summer as I wanted to work on the video. I didn't spend as much time as I wanted to. I had plenty of time, but again, motivation and burnout were a big thing. So I wanted to finish the video during the summer, I didn't finish the video in the summer. Luckily, as the semester rolled around, I started getting more motivation to edit it. And over the course of the summer, I started, shedding the perfectionistic attitude and being like, okay, yes, I know that I want this to be the best video I ever made. I know I want to do my 4 months of work on this project justice. I know I want to really, I want to get views. I want to get views. That's part of it too. Not all of it, but I want it to be the best video and I want it to get views. I know I want to do all that stuff, but I also have to be reasonable with what I can actually produce. Because if I edited that video with like super top of the line animated graphics, everything, extremely good writing, figurative language out the wazoo, the whole project, the whole video is a metaphor for classism or whatever. If I did something like that, like it would take me like until 2026. I'm not releasing a video in 2026 for a 2024 project. I have to be reasonable with what I do, basically. And so that's why when I started being like, okay, I'm going to make this best video I could reasonably produce. I'm going to get these replay shots. I'm going to do this. I'm going to learn a couple things along the way, but nothing too crazy. I still don't know everything about DaVinci Resolve because I don't think anyone knows everything about DaVinci Resolve. And yeah, as the semester rolled around, I got more motivation with my life more structured and things like that. And also another cool tip was putting the video, like dividing it up, chopping it up into little like segments, and keeping track of how many segments you have done out of like the whole thing. And that way you have like a quantitative percentage count of how much of the video you have done. That was pretty good for motivation because I could say, oh, I did 20% of the video like in last week or last month or whatever, and now I'm at 50% when I was at 30%. Like I'm making progress. Like I made more progress in like these last 2 months with school being there than I made during the whole summer. So that sort of shows how good that strategy is. Obviously not the best, because if I was a full-time YouTuber doing it as their job, I would probably have gotten this video done in probably 2 months. I think this would be a good 1 month or 2 month video for a full-time YouTuber, but I'm not a full-time YouTuber, so that's obviously not going to happen. I have to have a life too, gotta go outside, touch grass and shit like that, and not fail my classes. But yeah, so then I spent September and October locking in editing the video, and it's almost out. Yeah, yay, it's almost out. I haven't had everything done yet. I'm still waiting on basically 2 very minor things, and then yeah, that's it. I'll basically be done. Okay, so I guess that's all about I want to say for the making of the video. So let's do. So let's go into the shoutouts now. So obviously I have my early access reviewing team: Contranaut, Ewok Tub, JR5000, and Schmidt. And out of those 4, I really want to shout out Contranaut because he was the one who took that 11-minute segment of the video and said, like, even though I'm an engineer, this segment is still super boring, and if you want to get any kind of views whatsoever, you should probably like scrap this or heavily change it. And I respect that so much because a good advisor will tell you, what's wrong with what you're doing. A great advisor will make you question if what you're doing is even the right thing to do in the first place. So I love that. He's also been probably the strictest advisor. He's been saying like, oh, this part's boring, cut it down, cut it down, cut it down, cut it down, and and then I end up with a video that's like 40 minutes instead of 2 hours. So yeah, that's great. I also want to give a shout out to Red Penguin 111 because he had that very creative idea. He wrote most of the lyrics to the parody of that song. It's a parody of Psalm by the Reign of Kindo. He wrote most of the lyrics to that, and he made the note block cover. He's playing the cello to it. He's doing the lyrics, like he's doing the vocals, everything. It's crazy. And I mean, this poor guy. I spent so long editing this video that I had to get him to record the vocals twice. So yeah, he's really patient with me. Very cool guy. Love his Mabrek 5 speedrun. Go check it out. I hope that when I make my legendary speedrun, oh no, I spoiled the future video. I hope when I make my legendary speedrun, I can sort of match his level of editing somewhat. So that's cool. I also want to shout out Testable because, he was very good for editing inspiration. I love like the little skits he does at the beginning of his videos. Those are great. And obviously the intro was pretty much inspired directly by his style. So that's cool. Ewok also came up with the idea for the intro. So I have to shout both of them out for that. In terms of editing inspiration also, RecRap 2, although obviously he didn't tell me anything about this Redstone computer video. I don't even know him. He doesn't know I exist, you know. But I really liked the way he structures his videos, his narratives and stuff like that. And during that conceptual phase of the video, and even during like the early editing phase when I was a perfectionist, I had to like look at his videos and think, all right, well, like, I'll give you an example. There's a video of RecRaps where he beats Minecraft in 15 minutes and he works his way up to that. Now there are basically two directions he could go with that. The first is he could explain everything he did. So he could explain, like, here's how I find the BT, here's how I find the magma ravine, here's how I write the bastion, here's how blaze bedding works, things like that. And, you know, he could do that, or he could, what he actually did instead of being all nerdy with that, is he went like, well, here are, you know, so here's a brief overview of all the strategies I had to learn, and here's the, and here's how I learned the game and I got better at it, and I learned all the strategies and I picked up better strategies, and I eventually lowered my time until I was able to beat it in 15 minutes. And so basically that's the analogy there is, do I spend all this time explaining like how the ALU works, how the register file works, how this works, how that works, blah, blah, blah. Or do I just say, you know, at a high level, I planned this project out, I drew diagrams, I made the computer in creative, here's basically what these components do at a very, very high level. And then, you know, focusing more on the learning aspect and the survival aspect and the challenge aspect of it, rather than all the technical details. So yeah, that's how RecRap sort of indirectly helped him out. I love RecRap. He's such a cool YouTuber. And also, what was it? I think that's about it for editing inspiration. But for in terms of like Redstone help, MatBat is epic. He's so cool. Love his videos. They have been so helpful. His Logical Redstone series have been so helpful to me, because if it wasn't for like his stuff, instead of like 41,000 redstone, it probably would have been like 410,000 redstone. Like, he actually, like, his designs and his tutorials and stuff really helped. And I thought I like knew everything. Like, I was able to just take my hardware design skills and plop them into Redstone and just know everything and be good. And obviously that was not the case. Still had a lot to learn. There were a couple things about like Redstone and how computers work and do things that even my hardware design professors didn't teach me. So like, yeah, it's like, you know, pull the meme up, Harvard, Yale, and then it's like Logical Redstone Reloaded, right? So yeah. Speaking of MatBat, he has a series, an ongoing series called Let's Build a Redstone Computer. And it's and he goes over, well, how to build a redstone computer. And it almost obsoletes this whole supplementary video. So that's cool. Obviously, this supplementary video is still good if you want to learn how my specific redstone computer works, or how to program my redstone computer. But if you want to learn about how redstone computers work in general, or even how computers work, or just logical redstone in general, MatBat is the guy to go to. His Let's Build a Redstone Computer series, I've seen a couple of them. They're fantastic. Also, a funny fact, just to intervene, I spent so long during the conceptual phase and the editing and actually releasing the video. Spent so long, a year and a half technically, of this project being an idea. Spent so long that not only did RecRap build the calculator in Survival Minecraft, which is like kind of close to what I did, right? Not only did he do that, but MatBat, he built 2 computers. He did his whole Logical Redstone Reloaded series, and then he started this series. So like so much has happened in between me conceptualizing the project and me finishing the project that all that stuff happened. Not to say that like, oh, I'm mad because now it makes my video useless. Obviously my video still has a place in the YouTube content ecosystem or whatever, and I'm still the first person to build a Redstone computer in survival Minecraft. Let that be known. Because if you're curious, what RecRap built does not technically count as a computer. It's not a CPU. But yeah, obviously it's like, it's just funny that all that stuff happened in between me thinking about the project and me finishing the project. All right, what else? Shout out to the Reign of Kindo for making good music. Shout out to the professor who taught the digital logic classes, because if it wasn't for her and her classes, probably also wouldn't have done that, build that Redstone computer. So yeah, and I guess with that note, that's pretty much it. It's the end of the supplementary video. This is the end of the supplementary video. Yeah, don't really know what to say. Thank you so much if you've made it this far, or even if you've just skimmed through it, or thanks to everyone who stuck with me through the journey, this very long journey of not uploading anything for 8 months, just grinding out this project. I don't know. Thanks a lot. Thanks to everyone. So glad to finally be on the tail end of this project. And yeah. Okay, I guess I'm really out of words now. Thanks for watching, and as always, stay speedy. Peace.